In section 2.5, we are going to look at the transformation of functions. The objectives for this section are, after studying this section, you should be able to recognize graphs of common functions. So we are going to define 7 functions that you need to be able to know what the graph looks like and what the domain and range of that function is. We then are going to use vertical shifts to graph functions. We'll use horizontal shifts to graph functions. We'll use reflections to graph functions. We'll use vertical stretching and shrinking to graph functions. We'll use horizontal stretching and shrinking to graph functions. And then we'll graph a function involving a sequence of transformations. All right, so here are the 7 functions that are frequently encountered in algebra. The first function is the constant function, f of x equals c. C is a constant. The second function is the standard linear function, f of x equals x. The third function is the absolute value function. The fourth is the standard quadratic, f of x equals x squared. The fifth is the square root function, f of x equals the square root of x. The sixth is f of x equals x to the third, the standard cubic function. And the last function is the cube root function, f of x equals the cube root of x. It's essential that we know the characteristics of the graphs of these functions. So let's look at each one of these separately. The first function we are going to look at is the constant function, f of x equals c, where c is a constant. The domain of the constant function is the set of all real numbers. Now, that may seem kind of odd, but the input of this function doesn't matter. The output is always a constant c. So you can input anything, but what you're going to output is c. So the range of this function is the set that contains the number c. The function is constant. Remember from section 2.2, a function is constant where it's horizontal. Everywhere in the domain of this function, its graph is horizontal. So it is constant over its entire domain. And it's an even function. It's even because there is symmetry with respect to the y-axis. The graph to the right of the y-axis is a mirror image of the graph to the left of the y-axis. The next function we're going to look at is the standard linear function. We call this the identity function, f of x equals x, because the slope of this linear function is 1 and its y-intercept is 0. So it goes through the origin and its slope is 1. The domain of the identity function is the set of all real numbers. There is no restriction on what you can input for x. The range of the identity function is also the set of all real numbers. As you can see, the domain, the graph indefinitely goes to the right and left, and the graph goes up and down indefinitely. So the range is also the set of real numbers. The function is increasing over its entire domain. It's always rising from left to right. And it's odd. It's odd because it's symmetric with respect to the origin. So if I have a point 1, 1 on the graph of my identity function, if I input 1, I output 1. If I input -1, I should output -1. So there should be a point -1, -1 also on the graph. So this function is symmetric with respect to the origin, so it is an odd function. The absolute value function, f of x equals the absolute value of x. The domain of the absolute value function is the set of all real numbers. You can input any real number that you want into this function and take the absolute value of it. So you can input anything. So the domain is the set of all real numbers. However, the range is restricted. By definition, the absolute value is the distance a point is from 0 on the number line. By definition, the absolute value can only take on values of 0 or greater. So the absolute value can only take on the values of the positive, say this again, the non-negative real numbers. You can't take the absolute value and get a negative. So the range is the set of all non-negative real numbers. And you can look at the graph and you can see that the range, the minimum value for y would be right here. And that's going to be y is equal to 0. And what's the maximum value for y? Well, the graph continues indefinitely in the positive direction. So the way we write that is that the range of this function is the set from 0 to infinity, including 0. So we use a bracket, 0, comma, infinity. The range is the set of non-negative real numbers. The function has a portion of its graph where it's decreasing and a portion of its graph where it's increasing. The function is decreasing to the left of 0. So to the left of 0, we would represent that as x is less than 0. And it's decreasing because the graph is falling from left to right. The slope of that portion of the graph of this function is negative. So it's as x gets bigger, y is getting smaller. So the function is decreasing to the left of 0. So the way we write that is that it's decreasing on the interval from negative infinity to 0. At 0, the function changes direction and it starts increasing. So it's increasing to the right of 0. So where x is greater than 0, it's increasing. So it's increasing from 0 to infinity. And again, you'll note that whenever we discuss where a function is increasing or decreasing, we always use open intervals, no brackets. The function is even because there is symmetry with respect to the y-axis. The right-hand side of the graph of the absolute value function is a mirror image of the graph of the left-hand side of this function. Or you could also look at it in terms of what your input and what your output is. If we input into this function +1, we output +1. But if I change my input to the opposite, so if I input -1, I also output +1. So it doesn't matter if I input the negative or the positive, I output the same result. The next function is the standard quadratic function. We call this a parabolic function. So we use the word parabolic because this is a parabola. F of x equals x squared is the standard quadratic function. The domain of the standard quadratic function is the set of all real numbers. You can input any real number and square it. But what happens when you input a real number and you square it? If you square a number, it's going to force it to be positive. So again, the range of this function is the set of non-negative real numbers. You can't input a real number into this function and get a negative. You can't do it. So the range is the set of non-negative numbers. And the way we write that is from 0 to infinity, including 0. If you input 0 into this function, you will output 0. Any other input, the output is going to be a positive number. The function has areas where it's decreasing and increasing. The function is falling to the left of the origin, so it's falling where x is less than 0. Again, when we talked about minimas and maximas in section 2.2, we noted that if we have a relative minima, which we do on this function, the relative minima is at 0, 0. The relative minima is 0 at x equals 0. If we have a relative minima, the graph is decreasing to the left of that minima. It changes direction at the minima and then it starts increasing. So it's increasing to the right of that minima. It's decreasing because it's falling from left to right. When we're left of 0, the graph is going down. We hit 0 and it starts going back up. So it's decreasing from negative infinity to 0, and it's increasing from 0 to infinity. It is an even function. It's like our quintessential example of a function that is even. Again, the left-hand side of the graph and the right-hand side of the graph are mirror images, left hand of the y-axis and the right side of the y-axis. So to the left of the y-axis is a mirror image to the right of the y-axis. Again, if we talk about inputs, if I input 1, I output 1. If I input -1, I also output 1. So it doesn't matter if I input a positive or a negative, I get the same output. The square root function, this is the first function that we look at where there actually is a restriction on the domain. The domain of this function is the set of non-negative real numbers. Why is the domain restricted? Why don't we have the domain being the set of real numbers? Because in real numbers, you cannot take the square root of a negative. We know from chapter 1 that the square root of a negative isn't real, it's imaginary. So we're going to restrict the domain to the set of non-negative real numbers, because those are the numbers we can take the square root of in real numbers. So the domain is a set from 0 to infinity, including 0, because we can take the square root of 0, and we can take the square root of any number that's positive when we are talking about real numbers. The range is also the set of non-negative real numbers, because remember that root symbol means the principal square root. That is by definition what it means, and it will always be a positive value. The function is increasing over its entire domain. It increases from 0 to infinity, but we always talk about increasing and decreasing over open intervals. So again, we're going to talk about from 0 to infinity, not including 0. At x equals 0, the value of the function is 0. And then infinitely close to 0, to the right of 0, it starts increasing. And the function's neither even or odd because it doesn't have any symmetry with respect to the y-axis or the origin. The cubic function, the domain of the cubic function is the set of all real numbers, as is its range. You can input anything and you will output any real number. It's always increasing over its entire domain. The entire graph is always increasing, which means that as x is getting bigger from one x to the next, y is also getting bigger from one point to the next. So it's always increasing. And it is our quintessential odd function because we have symmetry with respect to the origin. It is the function that we use as an example of an odd function. If I input 1, I output 1. But what happens when I input the negative? When I input -1, I output -1. So that is the definition of a function that's odd. If I have a point that this is this distance from the origin, if I draw a line in the opposite direction, the same length, I'll hit a point on the graph. So it is odd. Our last common function is the cube root function, sorry. F of x equals the cube root of x. That's the standard cube root function. The domain of the standard cube root function is the set of all real numbers. I can take the cube root of any real number, positive or negative, I can take the cube root of it. The range of this function is also the set of all real numbers. I can input a positive and output a positive. I can input a negative and output a negative. And it's increasing over its entire domain. It's always rising from left to right. It kind of looks like it may be vertical along the y-axis, but it isn't. It's constantly increasing. And it is also an odd function. There is symmetry with respect to the origin. If I input 1, I output 1. The cube root of 1 is 1. Sorry about that. If I input -1, I also output -1. This cube root of -1 is -1. So there is symmetry with respect to the origin. So those are our 7 standard functions. You really do need to know what they look like and what their domain and range is. All right, let's talk about vertical shifts. Let's begin by looking at 3 graphs whose shape are the same. So we're looking at the standard quadratic function, and then we're going to do something to our standard quadratic function. The black graph in the middle is the standard quadratic function, f of x equals x squared. So we've graphed the standard quadratic in black. Now look at the blue graph. What's happening there? Well, the blue graph is the black graph, but it's been raised up. It's gone up, vertically upward. And what the equation of that graph is, g of x equals x squared plus 2. So the equation of this graph, g of x equals x squared plus 2, adds 2 to the right side of the standard quadratic function f of x equals x squared. So you add 2 to the x squared. You add 2 to the right-hand side. So each y-coordinate of each point of G is 2 more than the corresponding y-coordinate of each point of F, because you take the output of F and you add 2 to it. So each y-coordinate, you're going to add 2 to it to get G of x. What effect does this have on the graph of F? Well, it shifts the graph vertically up by 2 units. So the graph of g of x equals x squared plus 2 is the graph of f of x plus 2, or it's the graph of f of x being shifted up 2 units. So if you add a constant to the output of a function, then you're going to raise that function up. So if I take the function f of x, which is x squared, and I add 2 to its output, so I get x squared plus 2, that is the function shifted 2 units up. All right, now let's look at the red graph. What have we done? Well, we've moved it down. The equation of the red graph is h of x equals x squared minus 3. So what we're doing there is we're subtracting 3 from the right-hand side of f of x equals x squared. So we took f of x equals x squared and we subtracted 3 from the right-hand side of that function. So what happens to my y-coordinates? Well, all my y-coordinates, my outputs are going to be decreased by 3. They're going to be 3 less than the output of f of x. So for example, if I input 0 in f of x, I output 0. But if I input 0 in h of x, I output -3. So each y-coordinate in h of x is 3 less than the y-coordinate in f of x equals x squared. So what effect does this have on my graph? The effect is that it moves the graph vertically downward by 3 units. So the graph of h of x equals x squared minus 3, is the graph of f of x minus 3, which has the effect of shifting the graph of f down 3 units. Okay, so here is the definition of a vertical shift. Let f be a function and c be a positive real number. The graph of f of x plus c is the graph of y equals f of x shifted c units vertically upward. The graph of y equals f of x minus c is the graph of y equals f of x shifted c units vertically downward. Here is another graphic of this. Let f be a function and c be a positive real number. The graph of y equals f of x plus c is the graph of y equals f of x shifted c units vertically upward. The graph of y equals f of x minus c is the graph of y equals f of x shifted c units vertically downward. So if we take any one of our 7 standard functions and we add a constant to that function, we shift that function up. If we take any one of our standard functions and we subtract a constant from that function, we shift that function c units down. Okay, so look at this example. This is an example using the standard absolute value function. The standard absolute value function is that function that's shaped like a V. It has its lowest point at the origin. It goes through 1, 1, it goes through -1, 1, etc. Now, what does the graph g of x equals the absolute value of x plus 3 look like? Well, adding 3 to the absolute value has the effect of shifting every vertical point up 3 units. So when I add a constant to my function's output, then I'm shifting it up that many units. So each vertical point on the graph of my standard absolute value gets shifted up 3 units. Every point gets shifted up 3 units. Every vertical point gets shifted up 3 units. So what we have here is the graph of the absolute value being shifted up 3 units. If we subtracted 2, we'd shift the whole thing down 2 units. Okay, how about horizontal shifts? Horizontal shifts are the opposite of what you think they should be. All right, so let's return to the graph of our standard quadratic function f of x equals x squared. The standard quadratic function, oh, excuse me, I already read that. The graph of the function f is in the middle of the 3 graphs. It's the graph in black. By contrast to the vertical shift situation, this time there are graphs to the left and to the right. So a vertical shift, we move the graph up or down. A horizontal shift, we move to the left or to the right. Look at the blue graph on the right. The equation of this graph is g of x equals x minus 3 squared. So now we're taking 3 and we're subtracting it from each value of x before we square it. So do you see the difference? Let's look at the difference. Okay, our standard quadratic function is f of x equals x squared. Can you see this difference if we write g of x equals x minus 3, well, I can't write it. X minus 3 squared, and maybe h of x equals x squared minus 3. Do you see the difference in how we write that? So the first function, g of x, is a horizontal shift. The second function, h of x, is a vertical shift. We'll take the whole thing and we'll shift it down 3 units. So what we do is we take our input x and we subtract a constant from it, and then we do whatever the function's going to do to it. Okay, so what effect does this have on the graph of f of x equals x squared? Well, it shifts it to the right 3 units. So g of x equals x minus 3 squared equals f at x minus 3, and that is a shift of 3 units to the right. So if you subtract a constant from your input x, that is a shift to the right. And the reason it does that is because you actually have to shift the input to get the same output. So in the standard quadratic function, if I input 0, I output 0. But now, for this function, to get 0 for my output, I have to shift my input to 3. So g of 3 is 3 minus 3 squared, which is 0. So to get the same output for a given input, I have to shift it 3 units to the right. All right? So horizontal shifts. Does this seem strange that subtracting 3 in a domain causes a shift of 3 units to the right? Perhaps a partial table of coordinates for each function will numerically convince us of this shift. Notice that for the values of f of x and g of x to be the same, the values of x used when graphing g must be 3 units greater than those used in f. For this reason, the graph of g is the graph of f shifted 3 units to the right. So the original standard quadratic function, if we input -2, we output 4. To get the same output in g of x, we have to shift the input 3 units to the right. So the input now is not -2. We're going to shift -2 3 units to the right. So it's going to be 1. So to get the same output, the input of g of x must be 1. So when we subtract a constant from the input of a function, that is a shift to the right. What about a shift to the left? Now let's look at the red graph. The red graph is the graph of the function h of x equals x plus 2 squared. So now we're taking our input and we're adding a constant. What effect does this have on f of x equals x squared? This shifts the graph horizontally to the left 2 units. So h of x is equal to x plus 2 squared, which is f of x plus 2. So when we add a constant to our input, when we add a constant to our x, that is a shift to the left. When we subtract a constant from our x, that is a shift to the right. Add, shift left, subtract, shift right. So here's our definition. Let f be a function and c a positive real number. The graph of y equals f of x plus c is the graph of f of x shifted to the left c units. So if you add a constant to the x, you shift it to the left. The graph of y equals f of x minus c is the graph of y equals f of x shifted to the right c units. So if you subtract a constant from the input, that is a shift to the right. So let's again see if we can't contrast the difference between vertical shifts and horizontal shifts. Let's use a different function besides the standard quadratic. Let's use the cubic function. So if I have f of x equals x to the third, that is the standard cubic function. Okay, what happens if I take my function f of x and I add a constant to it? That is a vertical shift up. What if I take my cubic function and I subtract a constant from it? That is a vertical shift down. So the first function is going to shift it up 3 units. The second function is going to take the graph and shift it down 3 units. So it just takes the whole graph and moves it down, or it takes the whole graph and moves it up. Okay, let's repeat this. Now what happens if I do this? Let's make g of x equal x plus 3 cubed. You see the difference now? We're adding 3 to the x and then we're cubing that result. If I add a constant to my input x, that is a shift to the left. Okay, how about h of x being maybe x minus 4 cubed? Right? When I take my input x and I subtract a constant from it, then that is a shift to the right. So we can see the difference. On the left here, I'm adding a constant to the output. I'm adding a constant to the function. On the right, I'm adding or subtracting a constant from the input of my function. So I have my original function, f of x equals x to the third. In the second function, g of x, I've taken my input x, I've added 3, then I cube it. That's a shift to the left. H of x, we take my x, we subtract 4, and then we cube it. Now I'm subtracting 4 from my input x, and that is a shift to the right. Okay, here's a graphic that shows this. Let f be a function and c be a positive real number. The graph of y equals f of x plus c is the graph of y equals f of x shifted to the left c units. So when I add a constant to the input, I shift left. The graph of y equals f of x minus c is the graph of y equals f of x shifted to the right c units. So when I subtract a constant from my input, that is a shift to the right. Okay, so what are we doing here? We have the graph f of x equals the square root of x, so the standard square root function. And what are we doing? We have g of x equals the square root of x minus 4. So since I'm taking the graph of f equal to square root of x, and I am subtracting 4 from the input of that function, I'm subtracting 4. This is a shift to the right. I'm subtracting a constant from the input. So that is a shift to the right. And you take the entire graph of the square root function and you move it to the right 4 units. So this is what it looks like. The blue graph is the graph of the standard square root function. And I take that whole graph and I just don't change the shape of it or anything. I just horizontally shift it 4 units to the right. And I get the graph of the function g of x equals the square root of x minus 4. All right, what if we combine our shifts? So the standard quadratic function f of x equals x squared. What do I do to get the graph of h of x equals x plus 1 squared minus 3? Okay, so we're doing 2 things here. Let's go ahead and write our standard quadratic above it. Okay, so we are actually subtracting 3 from the input. And we're adding, we're subtracting 3 from the output. Don't listen to me. We are subtracting 3 from the output, but we're adding 1 to the input. So we're adding 1 to the input x, and then we're subtracting 3 from the output. Okay, so what effect does this have? Well, the adding 1 to the input has the effect of shifting the entire graph to the left 1 unit. And the subtracting 3 from the output has the effect of shifting the entire graph down 3 units. So the standard quadratic function, which is the standard parabolic function that looks like this. Oops. I'm going to get a pretty picture, obviously, in just a second. We take this whole thing and we shift it 1 unit to the left, and then we shift it 3 units down. So it gets shifted down there, and now it's going to look like that. So it's been shifted 1 unit to the left and 3 units down. So I've written kind of over the top of this, so let me do a little bit of erasing. So this is what this is going to look like. The standard quadratic function is the parabola that goes through the points 0, 0, 1, 1, negative 1, 1, etc. Okay, first thing I do, when I add 1 to the x, that is a horizontal shift to the left 1 unit. So you take the whole graph and move it to the left 1 unit. Then subtracting 3 takes the entire graph and shifts it down 3 units. So we take the graph that's in the middle and we just move the whole thing down 3 units. And now, instead of going through 0, 0, it goes through negative 1, negative 3, because you've moved it to the left 1 and you moved it down 3. So instead of going through 0, 0, which is what the original function did, now it goes through negative 1, negative 3. Every point gets shifted to the left 1 unit and down 3 units. Okay, so how about this one? How do we graph this? Well, we have the standard cubic function, f of x equals x to the third, which looks like this, goes through the origin, goes through 1, 1, goes through negative 1, 1. It looks something like this. Now, I should know what the graph of that looks like. That's the standard cubic function, and I do need to know what it looks like. All right, what am I doing to get h of x? Well, I'm subtracting 3 from x, and I'm subtracting 2 from the entire thing. So the minus 3 right there has the effect of shifting the entire graph to the right 3 units. And the minus 2, since we're subtracting 2 from the cubic part, that has the effect of shifting it down 2 units. So I move to the right 3 units, 1, 2, 3, and I move down 2, 1, 2. So it looks something like this. To the right 3 and down 2. All right, reflections. This photograph shows a reflection of an old bridge on a Maryland river. This perfect reflection occurs because the surface of the water is absolutely still. A mild breeze rippling the water's surface would distort the reflection. Is it possible for graphs to have mirror-like qualities? And the answer is yes. So here we have a reflection of the standard quadratic function. The standard quadratic function is the parabola that goes through 0, 0, 1, 1, and negative 1, 1. That's the graph that's in black there. And the other graph is the graph of g of x equals negative x squared. Do you see what we've done to f of x to get g of x? Have we multiplied f of x by negative 1 to get g of x? And the answer is yes. So what we've done when we multiply the function f of x by negative 1 to get g of x equal negative x squared, we have reflected the graph of f of x around the x-axis. So what happens when we do that, when we multiply the function by a negative? So the function f of x equals x squared goes through 1, 1. If we multiply that function by negative 1, we take each y value, each output, and we multiply it by negative 1. So the graph g of x equals negative x squared. If we input 1, we now output negative 1. It takes the entire graph of f of x and rotates it around the x-axis. It reflects it around the x-axis. For corresponding values of x, the y coordinates of g are the opposites of the y coordinates of f. So the reflections of graphs are defined here. The graph of y equals negative f of x is the graph of y equals f of x reflected about the x-axis. The reflection about the y-axis, the graph of y equals f of negative x, is the graph of y equals f of x reflected about the y-axis. So do you see the difference in the two? What have we done? The first one, a reflection about the x-axis, we took the entire function f and multiply it by a negative. So we multiply the output by a negative. The reflection about the y-axis, what have we done? We've multiplied the input by a negative. So if we multiply the output by a negative, that is a reflection about the x. If we multiply the input, x, by a negative, that's a reflection about the y. Okay, so what have we done here? The standard cube root function, f of x equals the cube root of x. What have we done to get h of x? We've taken the input x and we've multiplied it by a -1. So we're now taking the cube root of negative x. If I multiply the input by a negative, that is a reflection about the y-axis. Getting messy. Now let's look at the difference. Let's write a different one. Let's write g of x. If the negative's outside of the cube root, so we're multiplying the output by the negative, that is a reflection about the x-axis. Okay, so what does this look like? Well, the standard cubic functions, this thing that was always increasing, looks like kind of a squiggly line here. If we reflect that about the y-axis, we get something that looks like this. Let me clear my pen so we can see it. All right, so the blue graph is the original cube root function. And then when I take that function, I reflect it about the y-axis. I just take the whole thing and rotate it around the y-axis. So this part of the graph gets rotated around the y-axis and goes over there. And this part of the graph down here gets reflected about the y-axis and it goes over here. So now the h of x equals the cube root of negative x is the graph in blue reflected about the y-axis. So you get the graph that's in brown. All right, stretching and shrinking. So now let's look at these three graphs again. The black graph in the middle is again the graph of the standard quadratic function. F of x equals x squared. Now look at the blue graph. The blue graph is narrower than the black graph. The blue graph is the graph of g of x equals 2 times x squared, or 2 times f of x. F of x and x squared are the same thing. So it's 2 times f of x. So what effect does this have on our function? Well, each y coordinate is going to be multiplied by 2. For example, the standard quadratic function goes through 1, 1. 1, 1, right there. The function g of x equals 2 times x squared. Now if we input 1, we output 2. If we input -1, we output 1. But now on the blue graph, when we input -1, we output 2. So the effect of multiplying the output by a constant means that we are stretching the graph. We're making it we're making it narrower. We're taking the y values and stretching them upward. So if you multiply the output by a constant, that is a vertical stretch, if that constant's bigger than 1. Now the second graph there is h of x equals 1/2 x squared. What happens when you multiply it by a number between 0 and 1? Well, if you multiply it by a number between 0 and 1, the red graph on this graph, what effect does that have? Well, that has the effect of taking each one of my outputs, each one of my y coordinates, and dividing it by 2. Multiplying it by 1/2, dividing by 2 are the same thing. So each y coordinate gets halved. What's the result of doing that? If we multiply the output by a number between 0 and 1, that is a vertical shrink. It actually flattens the graph out. So if we multiply the output by a number bigger than 1, that's a vertical stretch. If we multiply the graph by a number between 0 and 1, a fraction between 0 and 1, that is a vertical shrink. So here are our definitions again. Horizontal shifts, vertical shifts, and reflections do not, got a typo there, do not change the basic shape of the graph. They remain rigid and proportionally the same, and they just get moved around. But when we stretch or shrink, we actually change the shape of the graph. So vertical stretching and shrinking, let f be a function and c be a positive real number. If c is greater than 1, the graph of y equals c times f of x is the graph of y equals f of x, vertically stretched by multiplying each of its y coordinates by c. If c is between 0 and 1, so c is greater than 0 and it's less than 1, the graph of y equals c times f of x is the graph of y equals f of x vertically shrunk by multiplying each of its y coordinates by c. So here's another graphic that represents this. Let f be a function and c a positive real number. If c is greater than 1, the graph of y equals c times f of x is the graph of y equals f of x vertically stretched by multiplying each of its y coordinates by c. If c is greater than 0 and less than 1, the graph of y equals c times f of x is the graph of y equals f of x vertically shrunk by multiplying each of its y coordinates by c. All right, so what do we do here? Okay, we have the standard absolute value function, which is that function that's D-shaped. It goes through 0, 0, it goes through 1, 1, it goes through negative 1, 1. What happens if I take that graph and I multiply it by 2? Well, this is a vertical shift upward, because what we're doing is we're going to take each output given our input and we're going to multiply that output by 2. So now instead of inputting 1 and outputting 1, we're going to input 1 and output 2. So it's a vertical stretch. It's going to narrow my V. So my original graph is in blue. That's the graph of the function, the absolute value function. F of x equals the absolute value of x. G of x equals 2 times the absolute value of x. I take each of my outputs from my input x, I multiply it by 2. So now my original function, if I input 1, I output 1. But now if I input 1, I output 2. So it takes each vertical coordinate and multiplies it by 2. Each y coordinate and multiplies it by 2. Okay, so last but not least, use the graph of f of x equals x squared to obtain the graph of h of x equals 1/2 times x minus 3 squared minus 2. So now you have shifting and shrinking. And in MyMathLab, this is pretty easy to do. When you start graphing in MyMathLab, it will open a dialog box where you can just type in what shifting is going on. So what shrinking or stretching is going on. So it's important that you're able to look at the equation and determine what kind of horizontal and or vertical shifts are going on, and if you're stretching or shrinking the graph. Okay, so let's just start and let's look. I have 1/2 outside parentheses x minus 3 squared. So this 1/2 right there is going to be a vertical shrink. It's going to take each y coordinate and shrink it by half. Okay, what is the minus 3 doing? When I subtract 3 from the input x, so I have x minus 3 squared, subtracting a number from x is a horizontal shift to the right. So that is a horizontal and we're shifting to the right 3 units. All right, the minus 2, so I'm subtracting 2 from the part of my function that's being squared. When I subtract 2, that is a vertical shift down. All right, so let me see if I can graph this. It's 2 units. All right, so let's just graph the original function in red, since I have my red pin here. Okay, so the original function's parabolic, goes through 0, 0, goes through 1, 1, goes through negative 1, 1. So it looks something like this, if I can draw it. Okay, now let's see if we can't do the shifts. Okay, so we're going to do the shifts first, then we'll do the shrink. Okay, so we're going to shift it to the right 3 units. I just noticed I spelled shift wrong. So we're going to move it to the right 3 units. 1, 2, 3. Okay, and then we're going to move it down 2 units. Okay, but then we're going to take that graph and we're going to shrink the vertical coordinates by 1/2. So it's going to go there, but now we're going to take that vertical point and we're going to cut it in half. And that's a terrible graph, but you get the gist. We're moving it to the right 3 units. We're moving it down 2 units. And then we're taking each y coordinate and we're cutting those in half. We're multiplying each y coordinate by 1/2. Okay, horizontal stretching and shrinking. Horizontal stretching and shrinking are used way less often than vertical stretching and shrinking. Typically, horizontal stretching and shrinking affects trigonometric functions. Most horizontal stretches or shrinks in algebra we can equate to a vertical. So you can, manipulate the negative sign, and you can then write it as a vertical stretch or shrink. But let's look at horizontal stretching and shrinking. I said negative, the constant, sorry. If f is a function and c is a positive real number, if c is greater than 1, the graph of y equals f of c times x. Now you notice you're taking the c and you're multiplying it times the input. Is the graph of y equals f of x horizontally shrunk by dividing each of its x coordinates by c? So if c is a number bigger than 1 and you multiply the input of that function by that constant, you actually take the graph and you shrink it horizontally. If the constant's between 0 and 1 and you multiply the input by that constant, that is a horizontal stretch. So for most cases, a horizontal shrink is a vertical stretch, and a horizontal stretch is a vertical shrink. So we can usually take the horizontal stretches and shrinks and make them vertical stretches and shrinks. Where it doesn't work is when you got things like trigonometric functions. You can shrink and stretch horizontally. We're in algebra though. Okay, so here is a diagram of this. Let f be a function and c be a positive real number. If c is a number bigger than 1, and the graph of y equals f of c times x, so you take your input and you multiply it by this number bigger than 1, that's the graph of y equals f of x horizontally shrunk by dividing each of its x coordinates by c. If c is between 0 and 1, the graph of y equals c times f of c times x is the graph of y equals f of x horizontally stretched by dividing each of its coordinates by c. Okay, so what are we doing here? We have g of x equals 1/2 times x, and then we're squaring it. So what are we doing to the standard quadratic function to get this new function? We're taking each input and we're multiplying it by so since we're taking the input and we're multiplying it by a constant, that's either a horizontal stretch or shrink. And since we're multiplying it by 1/2, we're multiplying it by a number between 0 and 1, that's going to be a horizontal stretch. So you actually take the graph and you stretch it out. And you stretch it out by 2. So each x coordinate gets multiplied by 2. Now this graphic says that you divide by c. And if I divide by 1/2, that's the same as multiplying by the reciprocal, which is 2/1. So dividing by a fraction is the same as multiplying by the reciprocal. So what you do is you take each x coordinate and you multiply it by 2, so you stretch the graph out. And let me erase my pin marks, and you can see what's happening here. So each of the horizontal coordinates are getting stretched out by 2. So the original quadratic function goes through the point 2, 4. The stretched function that you're multiplying the input by 1/2, the input is going to be 4 for the same output. So you take each x coordinate and you multiply it by 2. Okay, so what are we doing to this graph? Use the graph of f of x equals x squared to obtain the graph of g of x equals -1/2 times x plus 1 squared minus 2. So what transformations are occurring to your standard quadratic function? All right, so again, in MyMathLab, you have to tell it what transformations are happening. So you graph the original function, the parabolic function, the standard quadratic function. A dialog box will pop up and you type in what shifts, what shrinking and stretching is happening. Okay, so the +1 is a shift horizontally, is a shift to the left, 1 unit. If I add a constant to my input x, that's a shift to the left. Then we've got a -2 outside those parentheses. That -2 is going to be a shift down 2 units. I have a 1/2 outside here. That means I am going to vertically shrink this by 1/2. So each y coordinate is going to be multiplied by 1/2. So that's a vertical shrink. And then last but not least, I have a negative. And that negative is going to reflect. If I have a negative outside the function, I have a negative there. See, the negative's not next to the x. The negative's outside. So when the negative's outside, that's a reflection about the x-axis. If the negative's inside, that's a reflection about the y-axis. So since it's outside, that's a reflection about the x. So our four transformations that are occurring, we're taking the standard quadratic function, we're shifting it to the left 1 unit, we're shifting it down 2 units, we're multiplying each y-coordinate by 1/2, so we're shrinking it, and then we're reflecting it around the x-axis. Or we're pointing it downward. So this is what it looks like. The standard quadratic function, f of x equals x squared. I've shifted it to the left, I've shifted it down, I shrunk it, and I flipped it over. That are all the transformations of this standard quadratic. So I moved it to the left, moved it down, shrunk it by 1/2, and flipped it over. And that is the end of section 2.5.